Hey everyone, welcome back to Vector Analysis. Today we'll be starting to talk about vector differentiation. Let me remind you about the ordinary differentiation of a real valued function. Let's call the function f of x. And the way we used to define the differentiation of a real valued function is as follows. So the notation is that you write d dx like that. So remember d dx is like an operator, df over dx. Sometimes we say that it's not a fraction, although we have seen from the rules of ordinary differentiation that this sometimes can act like a fraction, but it's easier for us and important for us to remember that d dx itself is an operator. And the way it is defined is as follows. So there is a different type of notation, which is also written as f prime of x, and these two things essentially mean the same thing. And the definition was as follows. So basically you had to take a limit and you want to find out the derivative or the differentiation of f at a point x. So basically what you do is you simply take the difference between the values of the function at x plus h, where h is a small number, and f of x, and you find out the rate of change with respect to the argument. Now you do that by dividing it by h and by taking the limit h tends to 0. And that was the rule for differentiating a real valued function of one variable with respect to its argument. Our effort to find the ordinary derivative of a vector valued function follows the same approach. Let's say that r of u is a vector valued function. So of course, r is the vector and u is the parameter. So r is a function of u. So a vector valued function depending on a single scalar variable, where u is the single scalar variable. And we can simply follow the same pathway to find the derivative of this vector valued function. So we simply use the same notation. You put d du, another derivative operator, and you define it as follows. You take a limit, and just like before, you find out the difference between two values of the same vector but at different positions. So basically you take r of u plus delta u, where delta u is a small change in the value of u, minus r of u, and you divide it just like before by this change delta u, and you take the limit delta u tends to 0. Sometimes the change in the vector valued function is denoted by delta of r, and therefore then the same thing can be written like this: limit of delta u tends to 0, and you take that limit for this fraction delta r over delta u, and that is the derivative of the vector valued function of a single scalar variable. Diagrammatically, we can show this operation the following way. Let us take the vector OQ to be the vector R with its argument being u, and when it's being changed, the value of the argument changes from u to delta u, we have another vector, a new vector, which is denoted as follows: R of u plus delta u. And if you take the difference between these two vectors, you find delta r, which is again another vector, because if you subtract one vector from another, you get a third vector, which is simply the difference between the previous two vectors, namely the final vector r of u plus delta u. Well, the u shouldn't have an arrow over it. Sorry for that minor mistake. Minus r of u. And that should be the diagram. Of course, as u goes to 0, this point Q goes more and more towards P, and at the end point, yes, delta R tends to be 0, but also delta U tends to be 0 as well, so that its ratio remains a definite answer, which will be some other vector. Notice that the derivative of a vector-valued function with respect to its scalar argument is again another vector. So this would be another vector. In fact, it's a function of the same variable u. So you can write it as follows: dr over du, which is a function of u. And so since this is another vector depending on a real scalar variable, you can differentiate it again. And in that way, so basically you take this operator and ask it to operate on this vector dr over du. And this is going to give you another vector, provided that the derivative exists, of course, in the limit delta u tends to 0. If the derivative exists, then you get a second order derivative, and theoretically, this is going to be another vector with respect to u. So this will be a function of u as well. And in the similar manner, you can continue to define the higher order derivatives if they continue to exist. Notice that in our definition, we haven't decided the dimension of the vector, and now we'll be operating on a three-dimensional space, and we'll be applying this idea into the three space, basically in the Cartesian coordinate system, and we'll gain important mathematical and physical insights that can be then applied to different applications very easily. So the first place we should go directly from here is the derivative of a position vector that traces out a curve in three dimensions. Assuming that we have a Cartesian coordinate system like this, where this is the x-axis, this is the y-axis, and this is the z-axis, a curve in this space, which is being here denoted by C, will have a parametrization of a variable, let's call it u, and we'll be calling this a space curve. So C of u is what we call a space curve, because it's a curve in the three-dimensional space. So call it a space curve, as simple as that. But since we are going to describe it with respect to a coordinate system, which has been labeled as x, y, z, so therefore we, instead of one single function, will have three relations. So each of these points on the curves will then be, of course, denoted by a coordinate x, y, z. But now, since it's been parametrized, the curve is parametrized by a parameter u, these x, y, z's will also be functions of u. So the position vector that traces out this curve, let us call it r, right? Small r, which is a vector. This will be a function of u. And this can be explicitly written in this coordinate system as follows. So r of u is written as x of u, and then we'll be using the typical x hat basis vector, x hat, y hat, and z hat. So we have y as a function of u, so this is the coefficient, and then we have the unit basis vector y hat, and similarly we have z, which is a function of u, times z hat. In most of the literatures, of course, the basis vectors x hat, y hat, and z hat are replaced by I hat, j hat, and k hat, but they are all the same. So just be careful what notation you're using and just conveniently convert that as you might wish. So after a while, when the parametric value changes from u to u plus delta u as before, the new position on the curve that the position vector traces is this brown vector right here, and we can denote it by writing r of u plus delta u, just like before, and therefore we can find out the difference vector, sometimes also called the displacement, if we are really talking about spatial position. So let us assume that the positive progressing parametric value traces the curve in this direction. So of course, delta r will have the direction dictated by delta u. So what we can do is, like before, we can find out the difference vector, delta r divided by delta u, like here. And by definition, we'll have delta r, which is a function of u plus delta u, minus r of u divided by delta u, of course. And all we'll have to do in order to define the derivative, dr du, will be to take the limit of this vector we have just constructed here, so which is delta r over delta u. So remember, our original goal is to find out the expression for the derivative of the space curve. The derivative of the position vector that traces out the space curve to be completely correct in terms of the coordinate functions. And that part should be easy, as we'll see within a minute. So let's go step by step, follow this definition and procedure, and see what expression we find and what is the geometric interpretation. So in order to find out the explicit expression in terms of the coordinate, we already have the expression for r of u. All we'll need to do is to find out the expression for r of u plus delta u. And that shouldn't be a problem, because essentially is the same expression right here, except for the argument be changed to u plus delta u. And that is what exactly we have done here. All we'll need to do is to substitute this into the expression that we have above. So first, let us find out this expression for delta r over delta u, which is simply r of u plus delta u minus r of u, right, divided by delta u. Now, one thing we'll have to be clear is that when we substitute these expressions on the right-hand side, we'll notice that there are corresponding terms in terms of coordinate functions. So for example, from the first one, we'll see that we get x of u plus delta u. And from the next one, we see x of u. And the latter one will have a minus sign before it. So all we'll need to do is to replace the r by negative r and just plug it in here. Notice how it changes the signs of these coordinate functions, like we have just done here. And so we can pair up the corresponding coordinate terms because their corresponding basis vectors are the same. So based on the similarity of the basis vector, we'll just be pairing these terms up, and it's pretty easy to understand where we're going with this. So our first pair up will be x of u plus delta u minus x of u. Of course, the whole thing will have the corresponding basis vector x hat, and we'll be dividing that by delta u. We can do similar things for the other two pairs, which should look a bit like this. All right, notice I have separated the pairs, and in the first pair, we have x of u plus delta u minus x of u divided by delta u. And corresponding with the second one, we have y of u plus delta u minus y of u divided by delta u, and so on and so forth. Everything has fallen into the form. So all that remains is to take the limit. And the limit is simply this. We take limit delta u tends to 0. So what happens is that according to the laws of limits, this has to be taken in front of each of these square brackets, right? Because the limit distributes over addition. And if we do that, then this would be our expression. I hope now you can understand why I did put those gaps in front of the square brackets so that I can plug in the limits. But notice immediately what we have here. We have, for example, in the circled area, we have the derivative or differentiation of a real valued function, which is called x of u, and x is, of course, a scalar real valued function, and u is a scalar variable. So it's just a simple one-dimensional differentiation of x with respect to u. Likewise, this would result in the differentiation of y with respect to u, and this would be the differentiation of z with respect to u. So what we are left with is now extremely straightforward to see. So let us write it down. The derivative dr of du is going to be derivative of x of u with respect to u times x hat plus derivative of y of u with respect to u times y hat plus the derivative or the differentiation of the single variable real valued function z of u with respect to u times the orthonormal basis z hat. So since we have found this interesting expression, the expression for the ordinary derivative of the space curve, ordinary derivative of the position vector tracing out a space curve. Now let us ask, what is the significance? What is the geometric significance of this expression we have found right here? Well, it's the same as the geometric significance of the ordinary derivative regardless of the coordinate, because the coordinate is just an interesting expression or a convenient way to calculate things, of course, but the geometry is independent of that, right? So basically what we have here is, let us denote, for example, here, right? Here we have a point, let us denote it by P, okay? And we want to find out the derivative at this point, derivative of the position vector at this point P. So what we'll have to do is to draw a bunch of subsequent vectors for different parametric values. So basically we'll be changing the value of delta u, and we'll see where do the resulting secant vector, a vector like this, the difference vector, the displacement vector, go. So if we, for example, just bring the vector closer and closer, so for example, for half the parametric value, let's say the resulting position vector comes here, and so the difference vector is also changed. It's now in here, and the more we bring it down to this point R, we'll notice this difference vector looks more and more like what we call the tangent vector, right? So the last one I have just drawn, so probably I'll draw it again with a different color. Let's draw it with red. So this is the secant vector, but notice it looks almost like the tangent vector. So as we take the limit, this will be exactly the tangent vector to the curve C at the point P. And that is the geometric meaning of the ordinary derivative of the position vector that traces out the space curve. In the next video, I'll be doing some examples, so stick around and practice together and learn. I'll see you on the next video.